CBT Nuggets JNCIA series, Junos Software and Architecture. Well, you know what? We're approaching about the 1/3 mark of this series, and I think this is a good time for us to take a little bit of a departure away from the CLI, away from the configuration, operational mode and configuration mode, and let's focus on some stuff that, believe it or not, is extremely important as you get on the job there at Nugget Lab. It's not going to be enough to be able to know your way around the CLI on the router and the switch. You'll need to have an underlying architectural knowledge, the big picture. You need that big picture. You need that architectural knowledge, a little bit of that theory, because you're going to have to carry that with you as you go farther along in this enterprise. Juniper enterprise routing, enterprise switching, and security. So we're going to fill in some holes here, fill in some gaps. Now, I'm hoping that by this point in the Nugget series, which is about number 5, that you took my advice, that you made sure to go and look at either my Network Plus or Jeremy Chiara's ICND or James Conrad and his Microsoft network infrastructure, because I do want to make sure that you're kind of getting some parallel learning. Learning about the OSI model and layer 2 and layer 3 and IP addressing. Because a little bit later on we're going to come back to the drawing board here and I'm going to make sure that you understand everything you need to know for the kind of layer 2 questions and layer 3 questions for this JNCIA certification. Okay, so in this nugget, we're going to sit back and relax a little bit and just let me kind of take you on a journey, kind of starting at the beginning. Back when I got into networking, we're dealing with hubs. So we'll kind of look at, from hubs to routers, remind you how they work, kind of see the evolution of these products and where we're at today. We'll talk about routing features, general routing features, and then we'll look at the distinctives, the things that really set the Junos operating system apart from other platforms, from other vendors. I'll introduce you to Junos Enterprise Routing. Of course, we're going to build on this throughout this entire path, from JNCIA to JNCIS to JNCIP, and hopefully beyond to Expert. Then we'll look at some platform options. We'll go up there on a web safari up to the website, up to juniper.net, and we'll check out some of the products they have right now in 2012. And then I'm going to finish up this with a little exercise, a little kind of a fun little game. We're going to play Follow the Packet. Okay, we're going to kind of follow a little packet as it makes its way through layer 2 and layer 3 of a Juniper device. Sound good? This is going to be jam-packed with a lot of good information, a lot of test-relevant stuff here, so hang on. If you want to, take some notes, okay? This is kind of a little bit of theory, a little bit of lecture, but you're going to like it. It'll be a nice departure, okay? Let's dive in. Now, as you embark on this career at Nugget Lab, it's quite possible, and theoretically, you'll look back on this experience and go, I remember back when I was working at Nugget Lab and I was just starting out with Junos, and man, the stories I could tell you. Well, I have my own stories. I remember when I first started out in networking and I was getting experience for a telecommunications company, I did some side jobs. I remember I did a side job for a friend of mine who was an attorney, and I remember going into his office, and back then, back in the day, the way we put our network together is we had this kind of large, thick cable. And this large, thick cable kind of ran around through the office. Okay, it would go through the walls. We would open up little holes in the walls, and it ran through this office. And we would take these old personal computers, and from the network interface card, it had a little BNC connector, and we would have this cable that would tap into this wire. And so we had these PCs with these what we called vampire taps that tapped into this cable, and this wire had a terminator on both ends. And this was really true Ethernet, a true Ethernet bus, where all of the devices on this bus were sharing this wire. It was shared Ethernet. And so this device would send out an Ethernet frame onto this wire, this shared bus, right? Now, if another device was trying to transmit at the same time, this would cause a collision, which is not a good thing, okay? A lot of collisions and you have pretty much a poorly performing network. And so the more devices you add to this bus, the more contention that you have for this shared Ethernet, and the more collisions you probably have, right? So what would happen is if there was a collision, both of these devices, let's say this device here and this device here, they would stop transmitting. and they would wait. They would do this randomizer, this random function. They would wait a random period of time. Now, it was a very short period of time, but it was still a random period of time, okay? Then they would verify that this bus is idle, and if it's idle, they would retransmit. And also, when they do that, both the devices will send out a jam signal onto the wire, and it notifies all the other devices on the wire that are tapped in there's a collision. And so that's kind of how we did networking early on. And when you see these boxes like this, everything's in a box now. It wasn't always that way. So what we did early on with hubs, and these are also referred to as repeaters, by the way. This is all we had for a while, okay, back in the day. Back when we, walked to school in the snow with barefoot for 3 hours, whatever. So we would take this bus and we would basically put it inside of a hub or a repeater. And so it was kind of like a bus in a box, what we called it. And so even though you had devices that were plugging into these ports, so it was kind of a star topology, right? One central point with all these devices plugging in, it was still a logical bus topology. So physically it was a star, right? A central point with all these spokes coming off of it, but it was still a logical bus. And we were still contending for that Ethernet bus that was basically inside of the box. We call this shared Ethernet. And so there's distinctives about hubs and repeaters that led us to newer technologies like bridges and switches, to be specific. So way back in the day in that law office, I had that one cable, right? And that cable, there's a distance limitation with Ethernet. Back then it was just a few hundred feet, okay? And so in that one law office, what I had with that one cable was a CD. It was one big collision domain, right? Because all the devices, all the nodes on it were obviously contending for this shared bus, this shared Ethernet, so they were colliding. There was potential collisions. Every time a device wanted to transmit, there was a potential collision. So it's a collision domain. And by the way, everything on the bus heard everything, okay? All their network interface cards. Here's the problem. Larger companies obviously wanted to use this Ethernet technology, but they obviously had a larger geographical area, right? With a larger geographical area, you had to take this and, of course, put that bus in a box so that you could connect these boxes together, and they would allow you to extend and increase the size of your Ethernet collision domain. However, these boxes would need to repeat the signals and send them across this Ethernet to the next box, okay? So really what these devices are, these hubs and these repeaters, is they're OSI layer 1 devices. They're physical devices. They just basically take, this is my diagram for bits, okay? Zeros and ones with voltage, right? So up here is a 1, down here is a 0. Whatever we're using for our encoding and decoding mechanism, these are basically zeros and ones. And so we just take these zeros and ones and repeat them on this wire and then send them on to the next device, okay? And then on and on. So this information gets repeated. So we use these repeaters or these hubs to kind of create our network. And so you could get something, if you had the money, because they were expensive, man, back there. You could have one big collision domain in an office like this. And you had, as you can see here, you had 5 hubs or 5 repeaters. These were in little star configurations, but it's still, these are just little buses. Each one of these is a bus. It's just one big collision domain, right? Now, these devices, they did give us, some advantages. They got more intelligent. You could use protocols like SNMP, and you could find out information. And if a device, went down, one of these wires went down, this port could shut down. You had other things you could add to this to improve it. These vendors, were smart about it. But you still had one big collision domain, and we kind of had this, rule of thumb called the 5-4-3 rule. Basically, this collision domain had a maximum size, right? You could max out with 5 segments that connected 4 repeaters, and then only 3 of those could be multi-point. So you can see here in this example, I've got 2 repeaters that are multi-point, right? This has got 1, 2 points. This has 1, 2, 3 points. So, and we've got 1, 2, 3, 4 segments. So we're pretty much okay here, right? And there wasn't a hard and fast rule. It was just that your collision domain would degenerate in performance rapidly if you didn't kind of stick to these guidelines. These were very common devices, but they were really slow. Okay, they used what was called a store and forward mechanism. So they would basically store the entire Ethernet frame and then forward it on, out these other ports, right? They weren't intelligent, really, and there was no filtering like we get in modern day switches and routers. So it became obvious as bridges came around, okay, bridges and switches, why settle for this bus in a box solution with shared Ethernet when I can go to a bridge or a switch? And a switch really more defines what it does. I don't know why we really got the term switch, because it's really just a multi-port bridge. Okay, a switch is really a bridge. When it gets right down to it, it is a bridge. It is a multi-port bridge. But I think the industry term for these kind of became switches, because the truth of the matter is, switches and routers and security appliances, they all do switching, because instead of storing and forwarding the package, they can look early on into the frame and determine, what should I do with this? Okay, and that kind of defines what a switch is. They're fast, and they can figure out pretty quickly where this frame needs to go. So early bridges were a lot like this box you see here. Okay, some of the first bridges, what will we use these for? Well, let's go back to that diagram. Early on, we could take these bridges and we could put them in between these hubs and create collision domains. So now I had 1, 2, here's 1, 2, and 3 collision domains. So bridges were just simple boxes like that we could use when we had these limitations. But bridges were different, okay, because a hub or a repeater, it doesn't have any real knowledge, okay? These endpoints are the only ones that kind of spoke the Ethernet language of love. But when you add this bridge in there, well, this bridge spoke Ethernet, okay? So this operated at layer 2, the media access control layer. So we would add a header and a trailer to the data payload that came down, okay, that the applications were using. It framed it, okay, and in that framing it used that media access control address. So it would learn these MAC addresses from these devices that were sending these frames through here, and so then it would learn and find out which devices were on which collision domain. Okay, so you kind of broke up your collision domain into 2 domains or 3 domains. And so what we found out was this bridging technology, we could use this with hubs, but what if we took this bridging technology and applied it to our multi-port hubs and just started using multi-port switches? So we would combine the layer 1 activities of a hub or a repeater with the layer 2 activities of a bridge and make what we call a switch or a multi-port bridge out of it. And that's really where we have modern Ethernet networking now. Now, back in the day, bridges would do more than just that. You would have a bridge that would go from a token ring network, because that was a type of network, to an Ethernet network. So you could bridge 2 different networks, like the 802.3 network to the 802.5 network. And we still have bridges today. We have bridges now that are wireless bridges, where you have 802.3 networks that are bridged to a .11 wireless network, right? .11b, .11g, .11n. You've heard of these products. So we still use bridges, okay, but really to bridge between wired and wireless. So it's all about the multi-port bridge, all about the switch. So let's focus on that switch now, and then talk about why we went from switches to routers, because at some point switches had their issues and we had to put routers in between them, just like we had to put bridges in between hubs. So here's a Juniper EX switch. Remember how I said that a switch is really just a multi-port bridge? That's exactly right. If you have a workstation here, right, and it's sending traffic inbound on this first port and to another server that's over here on this port, right? Well, the frame comes in, and what this particular device actually does is it creates a bridge, an instantaneous bridge between those 2 ports. That's all it's doing. So it really is a bridge. It just happens to be one that can create all of these different bridges very, very quickly between all these ports. And we know that we can take a port and we can assign some identifier to it and put it in a VLAN and say, well, we want to group up these switch ports into their own VLAN and these switch ports into their own VLAN, okay? And if you want to communicate between those VLANs, we have to have some type of router process to move between them. That makes sense, right? So like we had bridges in between hubs, well, now we have routing processors or routers in between switches, right? Because of the technology of these modern switches, but this one has 48 ports on it. So this communication from this device to this switch is what we call full duplex. Okay, it's like a telephone, right? Both people can talk at the same time. These old hubs here, this was like a walkie-talkie, because think about it, that whole contention thing where you're contending for the bus, that's like a walkie-talkie. You know, when you had one as a kid, you were like, hey, Tommy, can you hear me? Over. Yeah, I can hear you, Michael. Can you hear me? Over and out, right? You had a protocol because you couldn't talk at the same time. Well, down here we have full duplex, which means on this wire going to this port, well, we can have two-way communication simultaneously. So if you have 48 ports, right, which we have here, that are all in full duplex, right? And each one of these ports supports 1 gigabit per second speed, which is, 1,000 megabits per second. Well, then the aggregate, okay, the aggregate throughput of this one single device here is 48 gigabits per second. Wow, that's amazing, okay? And you can even, kind of attach these and put them together in a switch fabric with Juniper switches and get amazing throughputs for all of your devices in your corporate enterprise that need access, okay? That's what gets us from, the hub to the switch now. And the switch is a very powerful device for aggregating all of the bandwidth between a bunch of devices, and basically you have an individual collision domain on each port, right? So there are no collisions, unless there's misbehaving devices and other problems. But for the most part, we're pretty much contention free. Okay, so that brings us to the reason why we had to introduce the router into the equation. And believe it or not, the router came after the multi-port bridge. So let's talk about why we need that router. Now, as great as multi-port bridges or switches were, they had some limitations. And if you think about this, think about the data that flows down from an application. We know that it gets encapsulated by, TCP or UDP, then that gets encapsulated by IP. When you get down to layer 2, it's basically framing all of that data that comes down and then gets passed back up at the other side. The problem is this header and trailer that we put on here, this is what we call metadata. Let me write this down here. That information in the header and trailer is data about data. Information, meta, which goes alongside of the data it's transporting. Well, here's the challenge. In the Ethernet header and trailer, there really wasn't metadata or information that provided techniques for dealing with large bridged or switched networks. So these bridges had a very low tolerance for loops, okay? Now we had mechanisms, spanning tree protocol, that we could use primarily for loop prevention, but the problem with early spanning tree protocol was the way that it dealt with loops is that it removed the redundancy in your network. So if you had more than one path from point A to point B, STP would just remove the redundant path, so you only had one single path. Well, that's great, but it doesn't really help us with performance. Also, we didn't get ICMP. We don't have things that do like ping and traceroute and other great features that we get from the ICMP protocol that we have with layer 3 or IP. Also, these bridges and switches, they weren't really good for connecting different network types. Usually you had a token ring network or an Ethernet network, and you had bridges between them. But if you wanted to extend out and connect buildings or across a city, Well, then you need to have wide area network protocols. Well, switches aren't good for that because, again, they don't have the metadata in the frame to deal with things like fragmentation. For example, if you've got one network over here that has a maximum size for what your packets can be, and a network over here that has a different size for what packets can be, well, you have to have some device that's going to take that larger packet and break it up into smaller packets, and to be able to, to keep track of it and put it back in its right order. Well, that's what routers are good at. But switches, again, there's no metadata in the header and trailer of the frame to deal with that. There's no real great filtering features for security, things like IP security, doing network address translation. That's not really there in the metadata. You can't differentiate different types of traffic, right? This frame, it just simply knows I've just got a bunch of data. It doesn't know what type of data it's transporting. Well, to be able to do differentiation and say, well, this is a voice packet, or this is a data packet, or this packet is part of a conferencing session, where you have to set priorities for the traffic and say, you know what, I'm going to give these packets a higher priority over these packets because these are sensitive to delays. So I'll give these voice packets a higher priority and these typical data packets a lower priority. Well, you don't get that kind of class of service with a frame. Again, why? No metadata. No metadata in the header or trailer to be able to identify that kind of information, right? And also, these multi-port bridges or switches were really bad what we call bum traffic, okay? If you had a lot of broadcast traffic, which meant all the devices are trying to talk to all the other devices, okay? Or unknown traffic, or if it was multicast traffic, which kind of came later. We'll talk more about that. That's our bum traffic. Well, if you have that kind of traffic and you're using just multi-port bridges, you're going to have poor performance, okay? So all of those things put together, also with the fact that we needed to connect networks together, switched networks together over longer distances, like wide area networks, for example, or metropolitan area networks, or leased line connections using the phone company, right? We needed some other kinds of devices to make that possible, and that's really where our routers come in. Okay, now that you have a fundamental idea of why we need routing, let's look at some routing features from a Junos perspective, right? Well, a good way to look at routing is just to look at a map of an area, because if you think about it, it's a lot like moving traffic, and it's a lot like getting from one point to another. So, for example, let's say the starting point in maybe my home is somewhere around, right over here, okay? And let's say that I want to get to, let's say, right here. Well, if you look at this, and again, this could be a town, it could be a city, it could be a campus of buildings, it could be, between a metropolitan area network, it could be international. I mean, it just doesn't matter. It's moving information from one point to another. And we know when we look at this, why we need routers in this environment. Number one, there's multiple paths, aren't there? There's multiple paths from the source of the traffic to the destination of the traffic. As you look at this, and you can even see how as the streets get wider, then we've got more capability for bandwidth, right? We've got more lanes. So we could call this, a 10 megabit per second Ethernet conduit. This could be a fast Ethernet, 100 megabit per second, and then over here we've got 1 gig of bandwidth up to 10 gigs of bandwidth, right? So we've got faster pipes. Now, just because we have faster pipes right here, for example, doesn't mean this is not a point of congestion. And at certain times of the day or at certain circumstances, I may want to reroute around this fast pipe and just stay on this 10 megabit per second conduit to get to this point, right? That makes sense. Or for some reason, if this particular conduit is down, I'll just come on this 10 megabit, go to this fast Ethernet, and then go this way. So, we can see why we need routing, because switched networks really couldn't do this because they're intolerant to loops and they don't like redundancy, right? They're only going to have one path at a time on a switched network. Also, if something's gone down, okay, along the way, then obviously I need to use tools like ping and traceroute. I need to use ICMP troubleshooting tools, and it's not easy to do on a switched network. Also, what if I'm going in between different network types? For example, let's say this is a dirt road, okay? This is an asphalt road, and this is a concrete road. You with me? Different types of networks. Routers are good for going in between different types of networks. Also, look at this freeway here. Let me clean this up. Think about this. As you know, in some larger cities, and for example in Phoenix, they have the far left lane, okay, of the highway is like a diamond lane. It's a carpool lane, right? So if you have more than one person in the car, or if it's an emergency vehicle, or if it's a city bus, they can go in that far left lane, which is going to move a lot faster than the other 2 or 3 lanes, right? So we get class of service. We can classify the traffic and say, hey, if you have a carpool or your emergency traffic or a bus, we're going to classify you and give you a higher priority and let you go in that fast lane. And that's what we could do here on this freeway. That's the kind of thing we can do with routing that we can't do with a switch. There's no explicit class of service capabilities really natively. Also, if I have to put up a security checkpoint here, okay, and only allow certain types of traffic through there, filtering traffic, maybe at 12 o'clock at night I'm going to have one of those checkpoints where we're looking for drunk drivers, right? It's a security filter. Well, we can't do that with switches either. Let me clean that up again and use this analogy. For example, the device at these checkpoints, if it's a switch, it can look at the actual license plate, right? It sees the license plate number. That's the MAC address. But that's all it can see. That's all the switch can see. It can't look inside to see the payload. A router, which has the layer 3 services, can actually go inside the packet or the car and get the driver's license information from the driver, which has all that metadata about the driver, about the payload, right? That's the information. So if the driver is the data and the driver's license is the metadata, the data about the driver, we can do a whole lot more of filtering, can't we? If we're looking at that and going, okay, I'm going to allow you through based on information in your driver's license or other information about the driver. For example, blow into this machine and see what number pops up. So that's what routers can do, whereas the switch is just looking at the license plate, the MAC address. Now remember, the first device that Juniper sold was an IP router, okay? An IP version 4 router. But it's important to remember that since they launched that product, all of the Juniper products that are based on the Junos operating system have at their core, at their heart, routing capability, routing processors. So whether it's a J series router, or a higher end series router, or an EX series switch like this one, or even one of their security gateways like this, it's going to have routing processes at the core. And regardless of the device, the principles of routing transit traffic in those devices is going to be the same. And this is where we get into the architecture, okay? And I know architecture to some people this sounds kind of boring, but it's very important. From a real world standpoint, it's important to understand the architecture because it is the foundation of all the devices moving forward. And as you move up to larger and larger platforms, you need to understand the architecture. It's also important from an exam standpoint. So we're going to talk about Junos distinctives and the architecture now. Now, one thing that Junos devices have is a strict partition, a strict division between the forwarding plane, as we can see down here, and the control plane. And if we think about the forwarding plane, this is basically what moves the IP or IP version 6 or ISIS traffic, okay? This is the routed protocols, okay? So the protocols that are routed. Up here in the control plane, we deal with a lot of things, including the routing protocols, okay? The ones that do the routing. So basically the control plane is in control of how we forward transit traffic through the device, the switch, the security gateway, the router. And one of the good things about, separating this control plane and this forwarding plane is that you've got a built-in protection mechanism if there's some overload in one of the planes. So if the control plane is overloaded with some type of denial of service attack, for example, then the transit or forwarding plane isn't affected directly. So we can have different solutions, different technological solutions for the complex signaling and routing protocols of the control plane, like OSPF or BGP, while at the same time being able to forward and perhaps do class of service marking on a lot of packets in the data plane. And we can see also from this diagram that we have the kernel here, which is basically the kernel Junos operating system, and different services, the chassis service, the routing protocol service, the interface service, the firewall service, and then of course an ellipsis here to other services. And each one of these services runs in their own memory space, kind of in their own memory sandbox. So if we have failure in one of the interfaces, like the routing protocol interface, it doesn't directly affect the other services. And you can see that we have things that rely upon the forwarding plane and the control plane, application layer gateways, firewall features, network address translation, virtual private networking features. These all operate in the control plane, whereas quality of service is going to be dealing down here in the service plane, with packets that come from the packet forwarding engine of the forwarding plane. And of course, supporting all of this are the physical interfaces, the physical interfaces of our device. Okay, so this modularity between the control plane and the forwarding plane, as well as all these individual processes that run in the control plane, are going to give us, well, the world-renowned stability of Juniper products. Also, it's easier to isolate faults. So we'll say fault isolation. It's easier to troubleshoot this separation, this partition. You've got each process in its own module, and rapid and flexible innovation, which is key to Juniper products. Now, we need to go one step further because we need to talk about how we route traffic, because we're really focusing on routers here, right? So the control plane, I'm going to go ahead and separate it here. The control plane runs on what we call the RE, or the routing engine. Down here we have the forwarding plane. You see our packet forwarding. This operates on the PFE, the packet forwarding engine. You can see we've also got a services plane down here. We'll talk more about that later. So here's how we get traffic routed, transit traffic, data traffic routed through our device, through our router. The routing functions, this is important because we have these two separate engines, the routing engine and the packet forwarding engines. But the overall routing functions are divided between the RE, the routing engine, and the packet forwarding engine. It takes both engines to accomplish this. The routing engine, the RE, its job is to figure out the best route to a prefix. And so a prefix, by the way, is just something like, let's say, 10.0.0.0/8. So all of the routers in the domain participate in that responsibility, and it's the routing engine that takes the input from dynamic routing protocols and static routing and other filtering that the admin does and figures out the best route to a prefix. Because what is the goal? Well, the goal is ultimately to deliver it to the most specific prefix, which is going to be an IP address. Let me show you what I mean. Let's say I'm over here at 192.168.2.23 and of course /24 network, right? The goal is to get a packet from here over to a server or a PC behind this router. But it's on a whole different network and it's several hops or several routers away. So using the routing engine, this router knows about the prefix 10.0.0.0/8. It knows about that, but that's all it knows about. This particular router knows about 10.10.0.0/16, which is more specific. So the packet's routed with the routing engine and the packet forwarding engine to this router. Well, that's all it knows, but it needs to get to the 10.10.10.0/24 network, which is more specific. So this network knows about it, it knows that, so it forwards the packet to that router. This router is over a WAN link, and it knows about 10.10.10.2.30. So it forwards it on to this router till ultimately it can be sent over to this PC, which happens to be on the 172.16.100.44/32. And so only this particular device here, this router device, knows about this network. And this was the ultimate destination of the packet sent from this device on this network. And so we see the process of getting traffic to ultimately the longest prefix, and the longest prefix is 32. Now, of course, this router could know about, the 172.16/16 network, and there could be other down level routers to get more specific here. Okay, I just wanted to give you an example. And so, by the way, this could also have been on the same network as this over here if my network is designed that way, for example. But you get the point. Obviously what we're doing is we're using this mechanism to move traffic across hops, across routers, to ultimately get to the end point, or the most specific prefix being /32, which is going to be some device that's typically connected to some switch, some layer 2 switch that either connects to this router, or this switch itself has some router process running on it. Remember, all Junos devices, all Juniper devices, have a routing at their core. So those network prefixes and the way to route to those prefixes are stored in a set of tables, and these are going to be in the routing engine as well as the packet forwarding engine. Remember, they both have tables, they both work together. Now we'll delve deeper into this as we get farther along into this Nugget series, but the main table, our IP version 4 routing table, is called the iNet 0 table, and you can see it right here, iNet.0. That's the IP version 4 routing table. And so again, the routing engine determines the best route to a prefix. This information gets passed to the packet forwarding engine, and then all of the transit traffic is then dealt with or managed by the packet forwarding engine, the PFE. Now, if the routing engine here, iNet 0, decides that there's been some change in the network through, let's say, a dynamic routing protocol, or you put in a static route or something, and if that demands some change in the way we route our packets, then we're going to send new instructions on to the packet forwarding engine, the PFE. Okay, here's a portion of the routing table. This is the iNet 0 table, so it's the IPv4 routing table. We can see there's 4 prefixes that have been learned here. Okay, so this routing table knows about 4 prefixes. You can see these little asterisks here are telling us that all the routes are active. Okay, 1.15.1.0 is a directly connected network on interface gigabit 000 or gig E000. Gig E000 has an IP address of 1.15.1.1. Notice it's local here, local via gig E000. We've got prefix 10.10.10.0/24. That was learned via the OSPF protocol from another router on gigabit 000, and then finally the prefix 192.168.100.0/23. This was added. This is a static entry. So we see 4 different types. We see a direct entry, we see a local interface entry, we see a dynamically learned one, and we see a static entry. So these entries are analyzed, and all of the active routes, which all of these are with asterisks, are sent to the forwarding table. So the routing engine sends these to the forwarding table. Then the forwarding table is going to be handed off to the PFE, the packet forwarding engine. So here's an example of a forwarding table entry with the show route forwarding table destination 10.10.10.1 command. As you can see here, our forwarding table doesn't have all the prefix attributes that we see up here in the iNet.0 table. It just has the basic information it needs to handle traffic destined for the 10.10.10./24 network. For example, the next hop and the network interface, gig E00. Now, how does the iNet 0 routing table determine what routes it's going to put in the forwarding table? Well, it has to be the active route asterisk, with the lowest cost, and that's determined with a variety of factors we'll learn about later, with the lowest route preference. This number right here, 0 and 0 and 10 and 5, is the route preference. So a locally or a direct network has the lowest you can possibly have, 0. Static has a route preference of 5, a little bit higher is OSPF. So the most reliable, the most trustworthy is a locally connected one. Next to that is an administratively added static network, and then after that or above that is the dynamically learned OSPF network. Now, once this is all done and all the prefixes get inputted into the packet forwarding engine, we can now deal and manage our transit traffic, our data plane traffic. If a packet comes inbound to the router, the destination IP address is going to be looked up in this forwarding table down here, looking for the longest match. Remember? So 10.10.10.23/32 is a longer match than 10.10.10.0/24. Remember my diagram from earlier, where each router is always going to look for the longest match. Once it finds that match, it knows what the next hop IP address is and the network interface, and it can send that along to a router that most likely has a more specific or longer match in its routing table and packet forwarding engine, right? That's the goal, to get this traffic like a letter from the post office ultimately delivered to your mailbox. Let's finish up here with the web safari, and I want to recommend that you go up to juniper.net and make sure that you understand, for example, the most recent Junos release, for example, which is 11.1 in January of 2012. By the time you're into this particular nugget, there may be a newer release than this. If we go back here and we go all the way back to, let's say, 9.3, okay? However, they've already end of supported 10.3, and we know this by getting their bulletins and their updates, for example. Now, I had to log on to see this, so I just skipped through my credential process. And you can see here's a JTAC technical bulletin, and it's basically end of life, end of support for Junos 10.3. And that was as of December 21st, 2011. So they're going to, you can still use the software, of course, and use the Junos, but they're no longer going to support it. And their images are removed from juniper.net. So you want to make sure that you always are updated on that. Okay, so 11.1 at this point in time, which is basically February 20th, 2012. Something else you want to make sure that you're going to do, and I don't want to embed this into my nugget because this obviously changes, you want to go to products and services here at juniper.net and make sure that you look at, for example, the routing products. And you can see there's so many products there, but make sure that you're, come and take a look at the different series. We're looking at the J series services routers, but there's so much more here. As you get farther along in Juniper Enterprise Networking, and again, remember, Enterprise Networking really just means you own the equipment. Okay, Enterprise doesn't necessarily mean it's some huge Hewlett-Packard campus. Okay, it could be just it's your enterprise, it's corporate owned, it's company owned, it's not a service provider. So we've got the M series, the MX series, and so all the way up to the the T series. And spend some time coming up here and looking at the devices that are there now. We're focusing, of course, on the J series routers, but you can learn more about those. And I'm dealing with the J2320 and the 2350, but we've got higher end devices as well, and so that's something you really need to do. And I don't want to embed any of this information into the nugget because it can change and there'll be new devices a few months from now. So I'm going to give you that responsibility to make sure that you follow up and understand. Now, on the exam, by the way, your exam will not have questions that are specific about different platforms like the 2350 versus the 4350. Okay, you won't get that kind of questioning. So don't worry about that from an exam standpoint, but from a real world standpoint, you just really got to know. Okay, now remember I told you early on that I'm going to reserve the right to make changes throughout this particular nugget series, and so we were going to do Let's Play Follow the Packet, but I'm going to go ahead and reserve that for the upcoming nuggets. Okay, after this we're going to have my Layer 2 Exam Essentials, the OSI Layer 2 and OSI Layer 3 Exam Essentials. I'm going to follow up this architecture and software nugget with those two, which is really natural. So it'll still be lecture-based, okay? But we want to get that core information under our belt because from that point on, we're going to jump into, pure configuration from that point on. So we'll pretty much power out the remainder of this Junos JNCI series with all configuration and deployment. So in the next couple of nuggets on Layer 2 Exam Essentials and Layer 3 Exam Essentials, we will follow that packet. I'll kind of go through it and we'll look at the Junos architecture and a particular packet from one device and then getting that packet to another device. So I'm going to reserve the right to put that in the upcoming nuggets. In this nugget on Junos software and architecture, we talked about from hubs to routers, and I think it was a little bit more exciting than that movie From Justin to Kelly. Okay. I never saw the movie, but this kind of sounds like it. From hubs to routers. And the routing features of, general routing features. Looked at some distinctives of the Junos operating systems. Talked about Junos enterprise routing in the sense that we want to understand how it works. Talked about the RE and the PFE. Took you on a web safari to look at the different releases. We're at 11.1 code right now. Some platform options. Make sure you do a web safari on a regular basis to make sure you understand the Juniper products out there that are offered. And then we'll do this one right here. We'll do in our upcoming nuggets. Well, I hope this CBT nugget has been informative for you. I want to thank you for viewing. Take it easy.